So now we'll turn our attention to dielectrics, which are essentially just insulators, or insulating materials, and the effect it has on the capacitance and why. So just in general, if we insert a dielectric, it's going to increase the capacitance, but we want to kind of understand like how that happens. So what you have here is just a standard parallel plate capacitor with positive on the left and a negative charge on the right. And this, as we talked about in previous videos, this creates a potential difference between the two, delta V, as well as an electric field that comes from the cancellation of the two. The addition of the two. And then also remember that the electric field outside of a parallel plate capacitor is zero on both sides. And so the idea here is that what happens. So this is with an air gap or a vacuum, we would say. Then we know that the capacitance is the permittivity, and that's the permittivity of free space. So that's what that's talking about, is like this is free space, it's just vacuum, times the area over the distance between the plates. So we know that if we increase the area, we can increase the capacitance. And if we decrease the distance between them, we also increase the capacitance. But now we're going to, again, look at what happens when we insert a dielectric. And so if we put some kind of material in here, so I'll just draw it as a big rectangle, so some kind of insulating material, which seems strange, but that's what it does. Then we have to think about what happens inside of this material, because even though it's an insulator, we can still have polarization, and that's the key. So we're going to have polarization. So inside of this material, because it's an electric field, or you could think about it in terms of the field, or you could think about it in terms of the charges. So in terms of charges, the positive charges are going to push all the negatives, they're going to attract the negatives. Remember negatives, okay. If we're thinking in terms of charges, it's going to pull the negatives towards it, and the negatives will pull the positives. In terms of the field, remember that negative charges move against the field, positive charges move with the field. So either way, we end up getting polarization within the material. So we'll get something like this. We get negatives on this side and positives on this side. So you can notice that the polarization is opposite of the charges on the capacitor. Now we can look at the electric field produced by this, because when you get polarization, that produces an electric field. And so we'll see that we get an electric field that is actually against the initial electric field produced by the capacitor. So what's the net effect? What's the net effect? It reduces the electric field, the E field in the capacitor. And now we can start talking about the effects of that. But this is the key. We insert a dielectric, it's going to be polarized, and that polarization reduces the E field inside of the capacitor through superposition. If we add these up, you can see this is going to cancel some of that. So we get a weaker electric field, and this has effects on the capacitor. Because if we come over here, we can see that number one, the potential difference is the electric field strength times the distance between them. Remember, this is the potential difference across a capacitor. So if we reduce the E field, then we're not changing the distance, so the potential difference has to go down. So if E field drops, that implies that the potential difference drops. And then we can come over here and we can say, well, if the potential difference gets smaller, then it's inverse to the capacitance, so the capacitance has to get bigger. So this implies that the capacitance goes up. And this is the chain of reasoning. We have polarization, reduces the E field. Reducing the E field reduces the potential difference, and reducing the potential difference increases the capacitance. Now keep in mind, this is not a potential difference that's applied. This is when it's fully charged, okay? It's not like if I hook it up to a 9 volt and I reduce it to 6 volts, that's going to change the capacitance. That's not what it means. It means that I've charged it up to whatever it could hold. And then we put in the dielectric, it's going to increase the overall capacitance. And so now we have a new equation for a capacitor, the capacitance when there is a dielectric. and that's going to be kappa. So we get kappa times epsilon naught times the area over d. So this right here, that's called the dielectric constant. So this is determined by the material. Let me look up some values for you. I don't know any off the top of my head. Well, here, I'm going to rewrite this just so that it's cleaner, so that we can label some stuff. So we'll get kappa epsilon naught area over d. So this is the dielectric constant. Dielectric. I can't spell today. Dielectric constant. And it's some factor that we're gonna change it. And actually, the table that I have is in terms of K, which is big K, which is this entire quantity. But you can see that, like, for vacuum, this has to be 1, so that we can get back to if it's just a vacuum. Other than that, it's going to be greater than 1. So we would have kappa is going to be greater than 1 for a material other than vacuum, because it has to make it bigger. And that's the basic idea. So yeah, that's dielectrics. So kind of understand the entire process of how it works. You know, we can use the equation once you have some numbers, but understanding that this kind of ties together everything, right? We have like the effect of charges on charges. So we get polarization. Polarization creates an electric field. Superposition of electric field reduces the electric field, which then in turn reduces the potential difference, which increases the capacitance. So it's a long chain of reasoning. So really take some time to kind of put this together in your head and try to explain it, you know, to yourself or maybe a friend or a parent or something like that. Just make sure that you really have it down.